Okay, a little more about projections. Standard projections. Government organizations define standard projections for their particular areas. So you've got geometric properties that have been defined in order to limit distortion, and it imposes some requirements that you have got uniformity for data exchange, quality control, and geometric distortion in a particular area that an entity would be interested in. The principal one is state plane coordinate system zone. So the United States is broken up. Each state has individual projections. For example, here New York has 3 standard projections. Pennsylvania has 2, and you can see that Pennsylvania's are sort of long and skinny, and the New York projections are kind of tall. So you can, by looking at these, you can kind of identify what kind of projection they are. The long, skinny, vertical ones are going to be transverse mercantile projections, and the horizontal ones are going to be Lambert conics. So if the state is sort of long versus tall, then you'll see divisions along that line. And if a state is kind of tall, you'll find projections that are done transverse mercantile. You'll also notice that these don't make a lot of sense. They've got big chunks cut out of them, and those are due to the fact that there's some populated area in a particular location where they want the projection to be constant around that populated area. So the cities, really, you can almost identify where the cities are by, well, these little notches are in the projections. So looking at Minnesota for an example, you'll define the spheroid in the central meridian. So the central meridian is the central slice down through that identifies this chunk, and the 2 parallels represented here by the first and first standard parallel, second standard parallel. And so what we get in this scenario is from here along this line you'll be accurate representation, and here you're going to be compressed, and there you're going to be stretched a little bit on that side. California, it's got a bunch, got 6 of them across California. And the requirement is that you are looking for less than 1 part in 10,000 within a zone for distortion. Universal Transverse Mercantile, UTM system. This is a system that was developed to establish a series of UTMs around the globe. Now these are not state systems. These are the UTM system, which each one is defined. Each zone is 6 degrees, and so correspondingly the center of the zone here for the zone 30, the 30 minus 11 is 117, so that tells you it's 117 west. So zone 11 would slice down through here and catch a little bit of California on the bottom side. The UTM system is set up would be a square grid, and it have no negative numbers, and so it'll read left to right, top to bottom, and so on. And the idea here was to separate the Earth into a grid of area, and you can sort of see the grids get larger as you go vertically here to try to accommodate those. So these UTM grid lines you'll see on topographical maps. Now this is probably an image that you're familiar with, perhaps have seen these before, but these indicators here on the sides of the maps will be the UTM coordinates. So as you can see, this is 606, 605, 95, 96 in the UTM coordinates. The UTM zones being an angular setup, what you've got is you've got a zone that's located by the meridian. So here's your central meridian, and they're 6 degrees in general, so they get narrower as they go up. Here's this zone 11N again, and what you get is coordinates that are relative to an origin that is 5,000 meters to the west of the zone, and a relative northing relative to the equator. So this northing is this particular number. So you can see the origin is here. The reason that the origin is outside of the zone is so that all numbers in the zone are positive. So we would be, for example, here, this is 0, and then you would be east of that 0 so many meters, and north of the 0 so many meters. Okay, so this is sort of an expansion of where that occurs down here at the 0 point. So the UTM zones for the United States are kind of shaped like this for projections. For example, New York is principally in the UTM 18, so you'll see a lot of the maps that are generated in New York will have that projection if they are trying to get the entire state or close to the entire state in the projection. And you'll also notice that they don't really correspond to a particular state. They correspond to this, even distribution around the globe. Nationally, the United States has their own standard parallel for projections, which defines the distortion amount around the United States in terms of how it's projected as an image. So we've got to render these 3D things down to a 2D map, and datum transformations give us a 3D to 3D, and if we want to go from one projection to another, we may need to both change how the projection is oriented and also change from one datum to the other. Sort of a visual here. This is transverse mercantile, so what you're going to do is get lines of true scale. So we slice a cylinder through the earth, but the cylinder is a little bit smaller than the earth. So we have a true scale here and a true scale there. And we take the transverse mercantile for the entire US, and that would be a true scale line here. And then we would be getting compressed. So these are distortions to make things smaller by 2% into the central. And then over here it's true scale, sort of cutting through Erie. And then as you move off, again you get distortion errors. The oblique stereographic projection. Here what you're going to do is take a plane and slice it through the earth, and so there'll be these sides of the map are going to be compressed going down, and over here they're going to be expanded coming out. So the line of true scale ends up being just a circle. So this would be sort of the approach if you wanted to map the poles. Typically Antarctica or the northern area, we use this projection. Don't really use it very much for the United States, but this gives you an idea of what it would be. If we sliced through a plane right here, the scale would get smaller as you come in, down to 1%, and then 1% and 2% as you expand out. The conics, Lambert conformal conic, again, the cone is kind of smaller, and it's going to intersect at these two lines. So with the United States, we've got true scale here and a negative there, and scale orders plus 2% here. So you can see in all of these projections, it's 1 to 2% that we shoot for, and it really depends on kind of what you care about losing.